They call me the physics man. That's what I am. Okay, so we're looking at the last practice problem for Unit 5. It's the E1 15.5 problem. And this is the challenge problem. And the reason why it's the challenge problem is because, well, it's set up a little bit weird, okay? So in our problem here, we have a home run that's just been hit. And it clears the fence 105 meters from home plate. And the fence is 4 meters higher than the height at which the batter struck the ball. So like wherever the ball was, 4 meters above that, 12 feet, is where the home run like wall is, okay? And we know that the ball left the bat at a 31-degree angle above the horizontal. And we want to try to figure out what is the speed at which the ball left the bat. So we don't want X, we don't want Y, we actually want the speed at which the ball left the bat. So let's draw a picture here. Here is the field of play. Okay, that is right here. This is 105 meters. Okay, and this is where the ball started, and where the ball ended was 4 meters up. So we know this ball is going to kind of like arc out, and then it's that's a pretty bad picture. It's going to arc out, and it's like just going to make it over. Okay, now we want this velocity. That's what we want. And we know it's hit at an angle of 31 degrees. I don't want the X component. I don't want the Y component. I want literally what was the speed of the ball as it came off the bat. I want the hypotenuse of that triangle. Okay? I don't want Vx. I don't want Vy. I want V. And I know that angle is 31 degrees. So let's just start with our roots, right? Let's just fill in what we can on the box. Here's what I know. I know that once the ball's hit, it's not going to speed up in the X direction. Okay, we're going to imagine air resistance isn't a thing, so the acceleration is 0 meters per second squared. We know gravity is going to pull it down, so that's negative 9.8 meters per second squared. What else do we know? Well, we know that the ball has traveled 105 meters away from the plate, and we know it's gone up by 4 meters. And that's it. That's all we know. That's not enough stuff. If we've been following along with these videos, we keep saying if you have 2 out of the 3 things in the box, where this is 1, this is 2, and this is 3, if you have 2 out of the 3 things, you're good. We have 1 out of the 3. Can't solve it. Over here, for our best friend, if you have 3 out of 5, we have 2. The only thing we know that could help us is that these times are linked. And if you ever feel like in a physics problem that you don't have enough information, maybe you need to link 2 equations together. So let's try that. Let's just try this out, okay? This is going to be kind of weird. Let's go up into our velocity triangle right here and just recognize something real quick. This y velocity, this would be equal to the full velocity coming off the bat times the sine of 31 degrees. This x velocity here would be the velocity coming off the bat times the cosine of 31 degrees. We just use SOHCAHTOA, we set that up. Now I still don't know what these values are because I don't know what V is, but I know this is a true statement. Okay? And this is why this problem becomes challenging. So let's just say this. Let's say that our y and x velocities are like this. This is just equal to V sine of 31, and this is equal to V cosine of 31. Now how is that helpful? Well, it's kind of not, but it kind of is. Because even though I don't know what V is, I know that these V's are the same. And now I have the 2 out of 3 and 3 out of 5 for each side. So let's just write some equations out real quick. On the left side, I always know my equation is going to be velocity equals delta x, or displacement, divided by time. And in this case, could I solve for a time here? Sure. If I solve for a time, that's just going to be delta x over v. So in our case, delta x is 105, and our velocity here, well, it's kind of written weird, but it's v times the cosine of 31. Not super helpful at the moment, because I don't have t and I don't have v, so I can't solve for anything. Okay, let's take a look at the y side. If I look at the y side of things, how could I solve for t over here? Well, I've got a vi, a delta x, and an a. There's t. This kind of looks like equation 5, right? So let's use equation 5, which states that delta x equals, and this is a displacement. When I say delta x, I'm really talking about like a delta y or a displacement in the y direction. We just call it displacement. If you want to write delta y, whatever. But this is equal to an initial velocity times time plus 1/2 times the acceleration multiplied by time squared. And this is where things get interesting. I know what time is equal to, right? So watch this. What numbers could I put in over here? Well, I know delta x, or the displacement in the y direction, is 4. I know the initial y velocity is v times the sine of 31 multiplied by t. And be careful, that 31's in there. It's closed. And then this is going to be plus 1/2 times negative 9.8 multiplied by t squared. Now, why does this matter? Like, I cannot solve for the v here because I don't have the t. But I kind of do have the t. Notice how I'm only missing 2 variables. I'm missing v and t, and I'm missing them in 2 equations. This means that if I link these equations, I can solve. So what I'm going to do is I'm going to take this, because this in blue is what t equals, and I'm going to put it in for t in both locations. That will mean I've eliminated t from this equation, and everything will just be in terms of velocity. And that's the velocity I want, just v, not vx, not vy, just v. So that's what I need to do here. Okay, and that's why this problem is so tricky. I'm kind of doing a simultaneous motion problem where I'm solving for times this way and then moving those times into one another. So if I go ahead and write this, I'll put it in green here. I'm going to have 4 equals v sine of 31, and then t is going to be 105 over v cosine of 31. And technically this, fractional amount goes across the whole thing. Okay, this is plus, well, 1/2 and negative 9.8 is negative 4.9, and then this is multiplied by t squared. And I want to be careful here because that's 105 over v cosine of 31. All of that is squared. Okay, so I'm going to simplify a little bit here. What I'm first going to see is that v and v, they divide out here, which is kind of cool. And you might not know this, but sine divided by cosine of the same angle, that's actually equal to tangent. If we thought about y as our y component and cosine as our x, this is like y over x here, and that can be thought of as a slope. And that's what tangent is. Tangent is a slope. So I could rewrite this here as 4 equals 105, because that's the 105, sine over cosine is the tangent, so multiplied by the tangent of 31 degrees, plus the negative 4.9, so that's like minus 4.9, and then I'm going to have this multiplied by 105 squared. So what is 105 squared? That's 11025, so 11025 divided by, and this square applies to everything, so don't forget that. So divided by v squared, and then also divided by, you got to write this correctly, it's cosine squared of 31. And the way I actually like to take care of this is I actually like to think of this as doing the following. Cosine squared of 31, it's like the cosine of 31 times the cosine of 31, right? It's not the cosine of 31 squared, because 31 squared is 961, and if you take the cosine of that, you're still getting a fraction. So it's like I have this here twice, okay? So be careful about that. We write that as cosine squared over the cosine, not over the 31, so be careful. At this point, I can technically solve this. There's only one variable I don't know. It's the velocity here. Everything else is a number. Do the numbers look weird, and is that velocity in the denominator? Yes, but I can solve this. So let's work this out one step at a time. What I'm going to do here is 105 times the tangent of 31. That is a number. So I'm going to have 4 equals, and this is a number. 105 times the tangent of 31 is 63.1. Minus, and then let's take, what is our numerator up here? What is 4.9 times 11,025? So 4.9 times 11,025. This is going to give me, in the numerator, 54,022.5 divided by v squared. And then what's the cosine of 31 times the cosine of 31? Or the cosine squared of 31? Well, that's going to give me 0.73. Technically 0.734, but like whatever, okay? So how can I go about solving this now? Well, let's subtract this value to the other side. Okay, that's by itself, so let's get it out of here. So let's subtract 63.1 from each side. So if I do this, 4 minus 63.1 gives me, on the left side here, a value of negative 59.1. Okay? And this will equal negative, and then now let's combine these together. Okay? So 54,022.5 divided by 0.73, that's going to give me 74,003. I'm going to drop the decimal, that's such a big number, divided by v squared. The negatives are going to divide out, they're going to go away, which is very nice, because if they didn't, then if I ended up having to take a square root because of the square here, I can't take the square root of a negative. It gives me an imaginary number. I don't want that. So how would this work? Well, I need to bring the v squared over to the numerator on the left side and the 59.1 underneath. So I could like multiply by v squared on each side and then divide by 59.1 on each side. So that will give me that v squared equals whatever 74,003 divided by 59.1 is. And what does that equal? It gives me about like 1252. Now I can simply take the square root of this value to find what v is. So the square root of 1252 gives me 35.4 meters per second. And that is my answer, okay? Give or take a little bit due to some rounding there, okay? So it was kind of a wild problem. It was very different than what we've normally seen because in this problem, we just didn't have a lot of information here. So we kind of took a wild guess and said, look, let's just say, hey, let's just call the y and x components v sine and v cosine, throw them in. Let's set up equation 1 and equation 5 for the setups here, for the x and y directions. And then let's do a substitution method to try to eliminate some of those unknown variables that we didn't have so that we could simplify this problem down. And in doing so, we saw that a lot of stuff started to cancel out. We were able to make a substitution. Sines and cosines turns into tangents, and then it's just math, 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 math. And now we get an answer. What's really cool is now that we have this initial velocity coming off the bat, we could, if we wanted to, we could solve for all of this. We could go back in and solve for the y velocity initially and the x velocity initially. And then we can find final velocities and we can find times. So if you wanted to, you could go back and do all that, but we were just looking for the hard part right here of how could we get this initial velocity coming right off the bat, that kind of weird value, okay? So definitely a challenge problem, but in the end, we are now finished with it. I hope you enjoyed that. I hope you're scratching your brain a little bit as you're going through it, but we were able to solve that out together. Okay, so congratulations for making it through, seeing how that worked. Until next time, adios and take it easy. Pew!